Okay, so we're going to get started. Sorry for the delay. You are?
Yeah, right.
So it's my great honor to have two distinguished guests here, and this is the first time they've been together in almost 25 years, I think. 1993, you said,
Yes.
right?
Mm-hmm.
So we're fortunate to have Al Worden, the Apollo 15 command module pilot, and who conducted geology from lunar orbit in July and August of 1971, and the geologist who trained him, Farouk El Baz. And I thought I'd just do some brief introductions, starting with Farouk. He was actually here at MIT training in geology, which I thought I knew a lot about Apollo and hadn't realized in 1963, 64, and 65, he was working on his PhD at MIT, which he received, I think, just a year or two later. And upon graduation from the Missouri School of Mines, he joined Bellcom, the group that was set up by Bell Laboratories to basically be the systems integrator and advisor to NASA headquarters during Apollo, and then served to train all of the Apollo crews, including the Apollo CMPs. So, yep. And right at that same time, Al Worden was at the University of Michigan getting his graduate degree. He grew up in Michigan on a farm. He went to West Point, graduated in 1955, served in the U.S. Air Force. Upon graduation, learned to fly airplanes, became a test pilot, served over in the UK on a tour of duty at Farnborough, where I last saw you.
Yes.
And then went to Edwards, to the U.S. Air Force Research Test Pilot School, where you were an instructor. So. Right. You went to Michigan as well for a graduate degree. That's okay.
Heaven forbid. Yeah.
MIT just celebrated the centennial of the AeroAstro department, and at the same time the centennial of the University of Michigan. Those are the two oldest schools in the field of aeronautical engineering. So you were both in school roughly at the same time. Farouk was here, you were at Michigan. So in the background here, we'll show some of the images. Yeah. This is you in front of a T-38, I think, training for the mission.
That's at Edwards.
And some of the guys you were picked with for the Group 5. Do you want to talk about that selection?
Group 5. I came back from the Empire Test Pilot School in Farnborough, England, at the request of a guy by the name of Chuck Yeager. Now, you may remember, those of you who are old enough, Jeff will remember this. Chuck Yeager was the guy who first broke the sound barrier in this country, 1947, in the Bell X-1. He went faster than the speed of sound. First time it was not the first time it had ever been done. Guys had done it before in airplanes, but they did it illegally, and they didn't want to tell anybody because they'd get in trouble. But he's the first guy to break the sound barrier in straight and level flight. He was commandant of the Advanced Aerospace Research Pilot School at Edwards, California. And about a month before my graduation from Farnborough, he and the school came over on a visit, and he came to me and said, I want you to come back and teach at the school. And I was just absolutely shocked, because I knew for a fact that he did not like educated people. He was like an 8th grade graduate in West Virginia, and you know what West Virginia is like. And he became a pilot in the Air Force, and he became an ace when he was 18 in Europe. He became an ace because, and he would be very honest about this, he became an ace because he had the best eyes there were in the sky. He could see airplanes miles away where nobody else could. So he became an ace when he was 18. He was a stick and rudder man, and he did not like educated people. So anyway, he came over and asked me, because he wanted me to teach a couple of courses, write and teach a couple of courses, advanced, like course on relativity and, you know, that kind of, and I said, I can't do that, because I'm already committed to going to a test facility in England where they were testing vertical takeoff and lift airplanes. And that's where the Harrier came from. It's out of that whole program. And how the tilt rotor and all that kind of stuff comes out of it. And I thought, you know, that would be a fabulous, fabulous assignment, testing a vertical takeoff and lift airplane. But one thing led to another, and they got me diverted, and I went back to Edwards, and that's how I got in. Anyway. Make a short story long. Bear with me. I speak a different language than you people because I went to University of Michigan.
So here's a great picture Al and Farouk together in the geology training for Apollo 15. Farouk, do you want to
No.
comment on that one?
Well, the one thing I could say about Al was that the fact that he was just the most absorbent of technical stuff and geological things, because most of the crews had absolutely no knowledge of the Earth or geology or environment or any of that. So Al would come in and would absorb it all and would communicate with me or ask me questions about how did you know this and why do you say that and what did you tell me last time about such and why is this? So he really absorbed the whole thing, and for that he became the best observer from orbit. He would look from the spacecraft all the way to the surface of the moon, and then he will pick up tiny little objects and differences in color, differences in texture, differences in, and he will convey them right away, knowing that we're waiting for that. So I salute him.
Well, I do remember Farouk had me trained to look for evidences of volcanic activity. And there are a number. If you look at the moon, you'll see lots of stuff that looks like it could be volcanic. It could be lava flows. It could be Schroeder's Valley and Aeronautics, and even where our landing site was, Hadley Rill, which turns out to be a collapsed lava tube. So long distance, there are lots of things. But back in those days, the geologists that we trained with were still arguing about whether the features on the moon were made by meteor impacts or volcanic activity. Two different sides of this whole thing. And they used to argue all night long about which one was right. Well, obviously the answer is somewhere in between. So we looked for volcanic activity, and as a matter of fact, took high-resolution pictures of it. Farouk jumped on it, and everybody looked at it, and as a result of that, they actually changed the landing site of Apollo 17 to go there. So there was some real value in observational work that we actually found the volcanic activity.
And we were talking about that a little bit at lunch. You want to go a little further on sort of the
on Apollo 15, yeah. We had about 16 sites, potential landing sites on the moon. I was secretary of the committee that selected the landing sites based on the fact that they are safe enough, they are flat, they are such as all of that. And we've been selecting sites one by one for very specific missions. And by the time Al flew, we had only about 3 or 4 left. And one of the places where I thought would be an interesting place was on the southeast corner of one of the large basins on the moon, because we thought that has darker material, and darker material may mean younger volcanics because it has not been modified by later impacts. That's why it is darker. That was the interpretation. So I included this as well as all kinds of other sites for Al's observation. So Al knew exactly what we meant, and he knew exactly what we say that for. And he went on looking from orbit, and he began to describe the things that he saw. And on that one site, he kind of emphasized the fact that it is fascinating. And he said, I see a whole series of dark cinder cones. These cinder cones remind me of what I saw in Arizona. The cinder cones are surrounded by dark halos, and he kept on talking about that at the time. Just for fascinatingly, the Apollo program director, Rocco Petrone, God bless his soul, he was sitting at the top of the MOCR, which is the Mission Control Center, and he walked all the way down the steps. And he came to my location and the center, and he says, Farouk, your student may have picked up a landing site for you. So it became a kind of an interesting story there. We did not count on that particular site right away. We had all kinds of other sites to consider for each and every mission. And then when it came Apollo 17, we definitely selected that particular site where Al had picked up certain features that would be interesting, may have some younger material. One of the only geologist astronaut was one of the people on the Apollo 17 mission, and the site was picked up for Apollo 17, and the astronauts on the surface started going there, and Jacques Schmidt, some of you may have known his name, is a fellow geologist, and he went over there and he talked about the orange soil, and this orange soil reminds him of fumaroles. So we thought that this, Al said that something about the dark halo craters, and now the geologist talking about fumarolic activity. Maybe that is very young fumarolic activity, like what we have right now in the American Southwest, with fumarolic activities that actually would color the soil with this orange color, as we have here on Earth. And we all began to think this way, and we all went to the press at the time and talked about the fact that Apollo 17 found very young material, and this might mean we have to go back to the moon because that's a different conclusion than all other missions, and this and this and that. And it turned out that that geological observation was wrong. At the time of the mission, I asked the Ron Evans, the command module pilot on the mission, and I told them, the guys on the ground saw this and this and that. Look from orbit and see whether there is any other location that has the same color. And he did look, and he saw the color, and then at the other end of that circular basin, he did see other impact craters with the same hint of color as that one. So I knew then right there that's actually, that is not a very specific place here, and maybe Jacques Schmidt's interpretation might not be correct. But in the meantime, the observation from Al was very critical to the selection of the landing site. And the observation also allowed us to think a little more about the types of volcanic activities on the surface of the moon, whether they're old, whether they're young. And the Apollo 17 mission was a very fine mission to bring out some of these. The collected rocks added a great deal to our understanding of the lunar surface in general. Thanks.
Just a comment. Farouk was part of the group that helped select our landing site. Our landing site was 27 degrees north of the equator, very far off the beaten track. All the flights before us had gone within plus or minus 10 degrees of the equator because we knew all the gravitational constants. This one was 27 degrees north. Yep, there's our landing site, and that's called Hadley Rill. In the upper right hand corner is Hadley Mountain. Now, Dave had to fly the lunar module over Hadley Mountain, which is 15,000 feet high, down to Hadley Rill. But the interesting thing is, Hadley Rill is probably a collapsed lava tube. That's what we kind of think. Now, a lava tube here on Earth is maybe 35 to 50 feet in diameter. Molten lava coming down the side of a hill. The top cools and solidifies, and then the molten lava flows out underneath it, and you get a tunnel that goes up the side of the mountain. Here they would be 35, 40, maybe 45, 50 feet, something like that. This one's 1,000 feet across and 700 feet deep. Shows you the differences in the mechanisms, the physical mechanisms that are different from on the Earth here than they are on the moon. And one other thing I want to say is, in their inimitable wisdom, they picked us a lovely landing site. Palus Putridinus. You know what that means? Stinking swamp. They had us landing in stinking swamp. Thanks.
We didn't name it this way. It was named before we were born.
I know.
So maybe picking up on that, so Apollo 15 was the first of the J missions that carried the lunar rover, carried greater supplies to do 3 days on the surface, but also the trajectory of the lunar orbit was changed from the prior missions were at a 60 nautical mile circular orbit before the landing sequence began on Apollo 15. It's the first mission to take the command module dock to the lunar module down to 50,000 feet. That was the night before the mission.
Right. We went into an orbit that was 60 miles high. And before we went to bed that night, we adjusted the orbit to 60 miles behind the moon and 50,000 feet over the landing site, realizing that the mountain was 15,000 feet high. So we went to bed that night. How you go to bed in space is you put shutters up at the windows to block out the sunlight, and that becomes night. And so you just, you curl up and you go to sleep. And I got up the next morning and I pulled the shade down from the window in front of me, looked out the front, and I'm looking up at the top of Mount Hadley. And it freaked me out. So I called Houston, Apollo 15. Oh, we're so glad you called. Oh, why are you glad? Well, you're getting a little close to the mountain. I said, I can see that. I mean, you don't have to tell me. I can see it. Where are we? Well, you've been dropping a little bit in your orbit, because we did not know the gravitational constants at 27 degrees inclination to the lunar equation, or lunar equator.
All the prior missions have been at equatorial.
All the prior missions have been in that band of plus or minus 10 degrees. So how low are we? Well, now we've figured this out because I had the right numbers in my book, which John kindly pointed out to me, because I would lie and tell you it was a lot worse than what it really was. But anyway, we're down to 41,000 feet, plus or minus 9.
46.
46, was it? 46,
yeah.
okay, 46,000 plus or minus about 9. Now let me tell you, you're all STEM students, I assume. And I have to tell you that anytime anybody that's being trained in science, technology, engineering, and math gives you a number with a plus or minus on the end of it, you know they don't know what they're talking about, right? So anyway, we figured about 9, so we're down to like 37,000 feet, and the top of that mountain was 15,000 feet. We're getting pretty damn close to the top of that mountain. So it did not take us but one orbit to get Dave and Jim in the lunar module off on their own. Now, should I tell us the rest of it?
Yeah,
okay.
keep going.
So I get them in the lunar module, and off they go down and land. And I'm in the command module by myself, and I'm approaching the Apolloon, 60 miles in the back, where I've got to add some velocity to circularize the orbit. So I get in the backside of the moon, and I did not think about this, but we have 3 couches in the spacecraft. One on the left, and the one on the left has a pressure pad that sets against the left wall, and there's a shock absorber on the right side of that couch. Then there's a center couch, and on the other side of the center couch is another shock absorber attached to the right couch, which has that pressure pad. And so you adjust all that string of material all the way across there, and you can kind of get the couches from bouncing back and forth because you put a little pressure on the pressure pads. Well, the center couch was out. The shock absorber is on a swivel. When I fired,
here's a view of that's in the training, but
when I fired the engine to circularize, and I forget how many feet per second I had to add, instead of looking at the instrument panel, I was suddenly looking out the left window. Because that couch, when I ignited the engine, that couch, because of Newton, went like this. And now I'm looking out the side window. You talk about freaked out. I was really freaked because I could not reach a single control. So thank God the computer worked. And it stopped at the right time, and I was okay. I've never told anybody that. Only 45 years later do I even try and mention it. They can't do anything to me now.
Speaking of the computer, could you talk a little bit about your training here at MIT when you came to the instrumentation lab?
Yeah, as you probably know, we had a navigation system on board that involved a sextant, much the same as the ancient mariners used. And we would take a couple of stars, or we'd take the Earth horizon and a star, or the moon's horizon and a star. Here's the deal. If you take a series of star pairs, the computer will then figure out your attitude. It knows what direction you're pointed. Then you go back and you do an Earth horizon star, and you do that a dozen times, and now your computer has got you figured out where you are in the Earth-Moon system, okay? And we used an XYZ system with the sun at the center and all that, so it was all mathematically possible to do. However, and I'll say this too, I had to deal with mission control coming back home. There's always a danger during a flight that you're going to have a failure. And it wasn't so much a lunar flight because you're only gone 2 weeks. But, you know, we're thinking ahead to say, you know, when we go to Mars, we're going to be a year and a half out there. There's always a possibility of a failure in the system somewhere. And one of those systems that could fail would be the radios. How do you get a crew back home? Now, just to back up one second. We had a computer that was probably the first of the interactive computers that were made that really worked, done by Stark Draper and his boys. And it was a fantastic computer.
At least
we
one
had,
of them sitting right there.
Yeah,
Don,
yeah,
Don
yeah, yeah.
Isles from
Yes.
Dave,
the
how are you?
Instrumentation Lab. Don.
Good, John. We had a total memory that we could load into that computer of 75K. Is that the right number? I believe 78K, okay. I won't quibble over 3. Yeah, okay. Well, I got more in this, right, than I had back then. So we could not load all the programs into the computer that we really would like to have there, right? They had to take a program out of the computer. Guess which program they took out? It was a program called Return to Earth. So anyway, I had to deal with mission control, and I said, you know what? They keep a state vector, which is XYZ and velocity XYZ and a time. And after a long period of time, they could really zero in on where we were within certain feet and feet per second and that kind of thing. And I said, you know, if we're really serious about losing a radio if we go to Mars, then we got to figure out how to get back home on board. We got a sextant, we got a computer, let us do that. So I worked out this deal with mission control, and I did all my own navigation on the way home. And the deal was that if I established a state vector on board with my own navigation, and mission control did theirs, because they're still tracking us, they had their state vector. If those two differed by a certain amount, then they would upload a new state vector for me. But if I stayed within the constraints of those requirements, then they wouldn't touch it. And we came all the way back home under our own navigation, even through reentry. And I think we're just as accurate as mission control would have been. So that was kind of the
In other words,
computer stuff.
no radar updates from the ground.
We didn't take any updates. No.
To the state vector.
We did our own, yeah. So I guess the point of that is, see, I don't know how Star Trek navigates, but I suspect we could do a pretty damn good job of it if we had to.
At the very end, I'll show you a famous Star Trek
Yeah, I know.
picture. But do you want to say a few other words? I have a lot of pictures I wanted to show your crew, the mission patches. There's Farouk training the crew.
Yep.
I guess
Last minute training, yeah.
Yeah.
Let me make a point. Farouk and I are training. He's coming down to the Cape or Houston or wherever, and we had not yet named our spacecraft. We pretty much had zeroed in on the lunar module as the Falcon because all 3 of us were in the Air Force, and so that was a kind of a natural thing. But we did not have a name for the command module. Farouk came through what used to be called Washington National, I believe.
Yes.
It's now Reagan. And he happened to stop by a bookstore. You know, they're all over the place when you go into an airport these days. And he bought a book on old explorers. And he brought that along with him, and we're looking through that book, and we find this page to Captain Cook, who sailed to the South Pacific in 1779, I believe, in a sailing ship called the HMS Endeavour, with the English spelling. And that became the name of our spacecraft, because we figured we were the first scientific voyage to the moon. So that was an appropriate name. So anyway, just a little side note.
Neat.
Very nice.
Yeah.
Were you involved in the design of the mission patch?
The patch, fun thing. We had, the other thing that we could do, besides naming the spacecraft, is we could design our own crew patch. We had hundreds of designs sent to us, mailed in, that we had to look at, and we didn't like any of them. So we went to a friend of a friend who was an Italian dress designer. And you probably wouldn't know who he's talking about. I mean, if you were here in the 70s and 80s, sorry, ladies, guy's name was Emilio Pucci. Now, Pucci was a very famous designer back in the day, and he did all his work in pastels and swirly pastels on silk, and I mean, his dresses were eye-popping, right? Well, Emilio also went to college in this country. He attended the University of Georgia back in the early 30s, and he got a degree in agricultural engineering. I thought it was something else until I really started doing some check, but it was agricultural engineering. So he goes back, he's going to be a farmer. He didn't like that, so he learned how to fly, And he flew through World War II as a fighter pilot in the Italian Air Force. And after the war, my bottom line in all this is after the war, he did what all Italian fighter pilots wanted to do. He got into ladies' clothes. And he did it very successfully. But anyway, we got him. You don't have to be a designer. I mean, just be a fighter pilot, I guess. Anyway, he gave us a design. It was rectangular with fluted corners, and it was all pastel colors, blues and greens and purples and violets and that kind of thing. And we looked at it, but what he gave us was the 3 stylized birds. And so we took those, we put them over the moon. In front of the birds is our landing site. That's a depiction of the landing site. And we made it circular, red, white, and blue. Now, the end of the story is, we're also told we could not use Roman numerals on our flight, on our patch. That had been outlawed, and I suspect the reason is, you take 135 shuttle flights, and if you're doing Roman numerals, those get pretty long after a while. So they had outlawed that, so we had to use numbers. We didn't like that. So if you look very carefully at the back of the birds, behind the tail, you'll see an interesting shadow pattern. Now, truthfully, we had to move some craters around, and we had to have the sun shining from both directions, but we got what we wanted. So there's an X and a V behind the tail of the birds, and that was our Roman numeral 15.
Excellent.
Yeah. There is some fun. You got to have some fun in the program, I got to tell you.
Speaking of fun, you had matching Corvettes.
Well,
there.
yeah, we had, there was a big thing about us all driving Corvettes back in the day. General Motors decided that they would lease us a Corvette for, actually, it was supposed to be for 3 months, and it turned out to be 6 months. I think I ended up having 12 different Corvettes along the way, one time or another. But we were the backup crew on Apollo 12. And Apollo 12, they were all Navy crews, and they had their 3 Corvettes, but they had them painted black and gold. I thought that was the most outrageous, utterly ridiculous color scheme I'd ever seen in my life. Just blah, right? So we got ours red, white, and blue. We were going to do them one better. A guy by the name of Ralph Morris, who was the principal photographer for Life magazine, got us together one day, and we all went out to the beach, and he wanted to take a picture of our 3 Corvettes with Lunar Rover in front. And of course, that's the 1G Lunar Rover, but that's how this picture came about.
Neat. So this is the Saturn V rollout.
Saturn V.
There's your.
Just a word about Saturn V. Largest object that's ever been launched from the surface of the Earth. We did it. We did it 50 years ago. 50 years ago. We flew the biggest thing that's ever been launched in history. We've not done it since. Tells you something about the mentality of the modern world, maybe. Saturn V, 363 feet long. Thrust, 5 engines put out, 7.5 million pounds of thrust. We were well over 6 million pounds on our launch. We were the heaviest launch in the program because we carried lots and lots of stuff, but we were the first ones to carry the lunar rover on the surface of the moon and carry a scientific instrument module into lunar orbit. And we had a lot of extra stuff because we were doing this for the first time. We didn't really know, how much we could cut down on stuff. So we were the heaviest launch in the program. This picture here, oh, that's launch, okay. Took us 12 seconds to get past the launch umbilical tower. That's an eternity when you're sitting out there with that 7.5 million pounds of thrust going out the tail end. That's an eternity, let me tell you. We were out there for 2 hours waiting for our launch. Not too excited. I went to sleep. Got about 45 minutes of sleep waiting for the launch. 15 minutes before launch, they woke us up and we did our final checks and off we went. Took us 13.5 minutes to get the 90 miles. Now we're getting into a physics problem now. Took us 13.5 minutes to get the 90 miles. We could not go any higher because we didn't have enough energy on board to go higher. Compare that, if any of you have ever seen a shuttle launch. Shuttle takes 8.5 minutes, Jeff, correct me if I'm wrong, 8.5 minutes to get to about 130 miles, or 140 or somewhere along in there, right? 8.5 to get to 140. It took us 13.5 to get to 90. We are in enough of the sensible atmosphere that we're running into molecules up there all the time, and we are very slowly decelerating. So we only had a certain amount of time before we either went to the moon or we came back home. And I forget what that time was now. But it seems to me, if I recall, it's about 9 hours, about 6 revs. We went around the world once, and it took us almost all the way around the world to get us back to doing what we were supposed to do, because we're all plastered at a window looking at the Earth going by. We finally got back to making all of our checks, came over Hawaii the second time, and fired our second stage engines.
Third stage.
Or third stage, excuse me, the S4B. We went from 17.5 to about 25,000 miles an hour, which is what you need to go to the moon. Now, I don't know whether you know the physics of going to the moon or not. It's pretty simple, actually. It's just throwing a rock in the air. If I take a rock and I drop it, what's that rock trying to do? It's trying to orbit the center of gravity of the Earth. That's exactly what it's doing. But it's not, because the Earth gets in the way and stops it. If I throw it that way, and maybe I throw it with some velocity that way, still trying to orbit the center of gravity of the Earth. But now it's going out further, okay? If I throw that rock at 17,500 miles an hour, it's still trying to get back to the center of gravity of the Earth, but now the Earth is curving out underneath it, and you never get back to the Earth. If I go faster than 17.5, then the high point of that orbit is going to start moving up, higher and higher and higher. And the more velocity I put on it, the higher that elliptical trajectory now is going to be. 25,000 miles an hour puts you up at a point where the moon's gravity becomes greater than the Earth's gravity. And now you're captured by the moon's gravity. So that's how you get to the moon. Apollo 13, a good example. They just did a figure 8 around the moon and came back, right? And it was all due to the changeover of gravity from the Earth and the gravity of the moon, and how they went around the moon and come back to Earth. About 25,500 miles an hour is sort of the magic number. And that gets you to a high point. The apogee is high enough so that you are now captured by the lunar gravity, and you go into the moon. Interesting thing was, well, there are a lot of things we had to do on the way, and we could talk about that all day long. I mean, how to eat, how to drink, how to poop, how to pee, all that kind of stuff. But, you know, that's all pretty basic kind of stuff. We never saw the moon till we were in lunar orbit. The reason is that we had to fire the engine, which is behind us, to slow down. Now, if you are in let's say an air-bearing vehicle that's moving around, you got these big engines that move around. If you're going that way and you want to stop, you turn that sucker around completely, fire your engines, and come to, you're decelerating along the line of travel, right? We had to do that to stay in lunar orbit. So we had to look backwards. We never saw the moon. And I tell you what, I thank God that Mission Control knew what they were doing. Because one little bitty error 50,000 miles out would have been pretty disastrous for us. So that's what happened. Anyway.
There's the Earth from about an hour away from.
Yeah, and anybody see where that is? Yeah. Let's see. Right here. See what that is? That's Florida, by the way. Just for information.
Is it?
You see South America. You see the deserts of Chile down on the lower left corner. And that's Florida peeking through the clouds up there. I keep this because that's where I live. So everybody will know. Okay, the moon.
Might be upside down, you said.
That's okay. This may be upside down. It doesn't make any difference. When you're out in space, there is no up or down. It doesn't make any difference. You get very used to looking at things from any attitude. It makes no difference at all. The moon. Okay, we've established that the moon, the things we see on the moon are made up of two different things: meteor impacts and volcanic activity. We can look at Schroeder's Valley, Aristarchus Plateau, Hadley Rill. We'll see some of the volcanism working. But the big dark circles you see on the face of the moon are meteor impact craters. And I don't know, have they age dated? It's like 4 billion years, right? 3 to 4 billion years, something like that?
3.9.
Okay, the meteor storm came through and hit the moon on one side. Each of those meteors that impacted the surface of the moon were huge And the energy of exchange was enough to liquefy the surface of the moon, we think. At least that's my interpretation, right? So when you're looking at the moon at night, you're seeing those dark circles, and we say, oh, that's the face of the man in the moon. Every single one of those dark circles is where a meteor impacted the surface of the moon. And those craters are 500 miles across. So you can just imagine the energy that was exchanged when these meteors hit the moon. Now, I don't have a picture of it, but I do somewhere.
We'll come to a few.
Oh, okay.
There's the CSM.
Anyway, the point is that those craters, our landing site was on the third wave of the meteor that impacted and formed Mare Imbrium, 250 miles away from the center of impact. And that third wave was still 15,000 feet high. The amount of energy exchanged is just unimaginable. So great. Do you ever wonder why one face of the moon always points towards the Earth? Anybody figured that out? Very simple physical problem.
But let's see with the MIT guys and girls
Yeah.
and girls.
Tidal locking.
No? Due to what?
Due to what?
Yeah.
So as the Earth's gravity pulls on the moon,
Oh.
the moon gets stretched by that, I believe.
What do you mean stretched?
Hmm?
What do you mean stretched?
It becomes not a sphere, right? It becomes somewhat of a
I think there's a simpler explanation.
Yes.
Those meteors dumped a huge amount of material just under the surface on one side of the moon. So what happens to the center of gravity of the moon? Moves towards that direction. Now you've got an offset center of gravity from the physical center of the moon, and Earth's gravitational field takes care of the rest. It's like a fishing bobber, and it's going to point that way all the time.
So the center.
That's my interpretation. Now,
Yeah.
Farouk might have.
No, that's fine.
We haven't talked about
The
this.
center of gravity of the moon is about 2 kilometers closer to the Earth.
Is that what it
It
is?
is not in the center of the moon. It is shifted this way, so it's locked.
Oh, I'm so glad now I have a number.
Yeah, 2 kilometers.
Thank you.
So here's some of the photography from
Yeah.
orbit. This is actually
Tell him about that one. Yeah.
This is a picture. This is a picture I took just before I come back home. This is called Crescent Earth. Somehow has gotten to be kind of popular with a bunch of people that I know. My original picture was a montage of two frames that I took. But to me, it's a very interesting picture because it reminds me that when you're at the moon, looking back at the Earth, it goes through the same phases that the moon was. We don't often think about that here because the Earth rotates all the time, and you don't think about, forget the rotation, but the sun angle on the Earth at the time is going to determine how much of that Earth rotating you can see. Which reminds me, there's another thing too. I'm just full of ideas here, but the Earth's rotation. If you were standing on the equator and you stood there for 24 hours, how far would you go? Anybody know? 24 hours, stand in one spot on the equator, how far would you go? You'd go all the way around once. That's 24,000 miles in 24 hours. What does that tell you? That tells you that if you're standing in one spot on the equator, you are moving at 1,000 miles per hour. Now, the Earth is rotating to the east. Why do we launch from the East Coast? That's just a simple physics problem. We're taking advantage of the Earth's rotation. At the Cape, it's probably 700-800 miles per hour. I don't know the exact numbers. But when I launch from the Cape and I launch to the east, I just got a kick of 700 miles an hour, added on to whatever I got to do. If you're launching from the West Coast going that way, now you got to make up to 700 miles an hour plus another 700 miles an hour to go into a retrograde trajectory. Okay? That's the secret. Now, there's some interesting stuff about this. There's a guy by the name of Jules Verne. You probably heard of him. He's an old guy now. He wrote a book back around 1900 called From Earth to the Moon. Has anybody here read it besides me?
No,
Okay,
everybody
great.
else has to read.
Very interesting book. He puts 3 guys in a spacecraft. He sends them to the moon. He brings them back to Earth. They come through the atmosphere. They land in the ocean on parachutes. My God, does that seem familiar? You know, we picked that up in the Apollo program. That's exactly how we did it.
Launches from
More coincidences than that.
Launches from
Launches
Florida.
Florida.
His launch site was
From
just east of Orlando, which is the same latitude as Kennedy Space Center.
And he has all the 3 astronauts get drunk as soon as they get there.
Well, they have, yeah. But the interesting thing was, well, it was the Gun Club, which was in Orlando, right? They're the ones who underwrote this big thing going to the moon. The interesting thing was he didn't know anything about rockets. So he had to fire them out of a cannon. I can't imagine being fired out the end of a cannon at 25,000 miles an hour. I'm not sure there'd be much of me there. I think I'd be mashed against the back. But anyway, that's what they did. So, but again, he took advantage of the physics of what he was trying to do. He launched to the east at a latitude of 27 degrees. I'm surprised he didn't launch them from the equator, but I think the Gun Club being in Orlando, they didn't have the wherewithal to get everything down to the equator. That would be my guess.
And it was the Columbiad, too.
It was the Columbiad, right.
So some scenes of lunar orbit, which maybe you could talk about Tsiolkovsky and some of the observations that the crews made.
Tsiolkovsky, interesting. Please correct me, Professor.
You know I will.
Yeah. Tsiolkovsky is a typically small crater caused by a meteor impact. Now, a meteor impact acts exactly as a stone would if you dropped it in a pond. Same thing. First thing that happens when a stone hits the water, you get a rebound feature that comes up. When the rebound feature subsides, you get the waves that move out, okay? Tsiolkovsky is an example of a meteor that impacted. What you're looking at is the rebound feature, but there wasn't enough energy exchanged to allow the total process to continue, so we're still seeing the rebound feature sticking up from the center of the meteor impact. And, interestingly enough, the walls around Tsiolkovsky are about 15,000 feet high. These are pretty big objects.
So you carried a mapping camera, and these are a few of the images from,
I carried,
from the mapping camera.
Yeah, this is Aristarchus Plateau, I believe. You can see some volcanic activity. These are lava flows that have eroded the surface of the moon. As a matter of fact, this area here back in the 60s, I believe, they actually saw some volcanic activity. They actually saw some smoke coming up. So it was is in this particular area. We don't have a picture of it here, but the most interesting pictures I can remember taking on the moon are right at where the sun goes out of sight. Shadows get very, very long. And if you've ever read any of the conspiracy theories about all these things on the moon that you know, the people who write the articles, they know they're man-made. Well, when the shadows get long, things look very different. And you can make out all kinds of faces and triangles and rectangles and all kinds of things based on the shadow pattern. I remember there was a very famous picture that was just shown here a couple of weeks ago of a camel caravan. Maybe some of you have seen this, National Geographic. Some of the most interesting pictures ever taken. A picture taken from overhead of a long string of camels walking across the desert. Have you seen that? And you see all the camels in dark. They're all in dark. So you read the bottom line at the print and you say, all the dark that you see is a shadow. What you're seeing is a white line at the base of the shadow, and that's the camel. You're looking straight down on it. You don't see it. All you see is the dark stuff. So these shadow patterns are very, very important to geologists and the people trying to describe what the moon's like. Very important.
These are some from the far side.
Yeah, these are some more of the, you can see that was a crater, which is almost totally covered with molten lava. which is, of course, solidified now. But you're looking at the ring around it, and the center of that is all solidified, what was at one point molten lava. Very smooth. When we look at the moon, we see the dark faces on the moon, right? Those are not because it's dark material. It's because of the texture of the object you're looking at, I believe. Isn't that right?
Yes.
Okay, the dark circles you see are caused by the texture of the surface and not because the material is darker. Moon's materials pretty much looks the same whenever you look at it. If you're looking towards the sun, and I've heard this from other guys, but if you're looking towards the sun, it's kind of brown. If you're looking away, it's gray, or the vice versa. I forget now which. So it all depends on where the sun is when you're looking at it. But the moon is pretty much monochromatic.
This is one of the impact craters from the mapping
there's an
camera.
impact crater.
Timokaris.
When we studied, here's an interesting one. When we were studying geology, we had to know how do you figure out, how do you decide the difference? If you see a feature like this, how do you decide that it's a meteor crater or it's volcanic eruption? Because we have things here in this country, especially down in Texas, called calderas that look very much like a meteor impact. Very much. Now, so you got to learn how to differentiate the meteor craters from volcanic activity. So one of the stops we made in our geology training was down a meteor crater down in Arizona. When a meteor impacts, the material comes up and it flows out. Okay? Now, if I look where that rests on the ground, if I dig down through that, I will see old material, new material, and then old material. Okay? You can age date it all the way down. Because what you've done is you've folded over a flap of the earth, so you're looking at the stuff underneath. A volcano, conversely, when it spouts everything, it all comes down sequentially. So you don't get that reversal. Everything you see in a volcano, the oldest is on the bottom and the youngest is on the top. But on a meteor crater, it's the other way around. The oldest is on top, then you hit the youngest in the middle, and then the oldest on the bottom. Just as, that's a simple way, but you'd have to drill through it. And Dave Scott on my flight kind of put a core sampler down, I don't know, 6 feet maybe, to check for stuff like that. Yeah.
There's actually Dave on the surface.
That's Jim Irwin.
Oh, Jim Irwin.
Yep, that's Jim Irwin.
You were able to spot
I think.
Oh, it's got the red stripe.
No, it's got the red stripe. That is Dave. Yeah, okay. I had a 10-power monocular, and if I got set up exactly right, landing site's over there, and I'm coming over. If I'm set up exactly right, and I catch them early, and I don't change anything, then I can track them all the way through.
Mm-hmm. Which you did.
Which I did several times. Yeah. But there were times, most of the time, I'd get partway up and I'd lose sight of them, and then I could never find them again. Mm-hmm. We're going too fast. We're going 5,000 miles an hour at 60 miles. So it's very tough. Now, it makes me think of, have you all heard about Cooper's treasure? Anybody heard about that? You've heard about that?
No.
Well, supposedly, Gordon Cooper, from orbit, drew maps of treasure ships. Now, he's going at 17,500 miles an hour at probably 130 miles. I find it amazing that he was able to spot them, draw them, and look for them the next time around. He didn't have anything else to do, I guess. I don't know. But I'm amazed. Jeff, did you see that, Jeff? It's on Discovery Channel. It's called Cooper's Treasure. And there's a treasure hunter who's got those old maps, and we're going to find out if that's real or not.
Under the ocean?
Yeah. Well,
Yeah.
Jeff, that was exactly my reaction.
Yes.
Oh, yeah, it's under the ocean. Yeah, oh yeah, yeah, yeah. And he's going 17.5 over it. I had a hard time at 5,000 finding those guys and keeping a track, keeping track of them, looking at them.
With no atmosphere.
Yeah, with no atmosphere, which is better viewing. Absolutely. Yeah, anyway.
So this is the rover on the edge of Hadley
This is
Row.
the rover. We had, our rover is electric powered, 4-wheel steer, 4-wheel drive. It had a joystick. You push it forward, you go forward, you pull it back, and you brake, and you pull it back a little more, and you go backwards. You twist it right, and wheels turn to the right. You twist it left. And you had switches, so you could steer by the front wheels. You could steer by the back wheels. I mean, any combination you want. The future car, we're going to see a lot of them on the roads, I think. Stuff like that. We're already seeing electric cars.
Sure.
All we're waiting for now is the joystick. And I suspect that's coming. It'll be coming. And it'll make it a lot easier. In the first place, when you get into the car, you don't have to worry about getting around the steering wheel to get in, because there won't be anything there. So anyway, it's going to be fun. This thing was designed by Boeing, and we were going to carry it on our flight, but there was a problem with the lunar module. The Boeing couldn't make it work. We happen to know some people at General Motors, so we called the chairman of General Motors, Ed Cole, who was a friend, told him what the problem was, and he said if Boeing would agree to it, send it down to Santa Barbara, where our research station. And I'm trying to think, who was in charge of Santa Barbara back then? It was one of the NASA administrator. He came on as the NASA administrator.
Tom Paine?
No, it wasn't Tom Paine. It was, anyway, Woods Hole.
Bob Frosch?
Huh? Frosch. Yeah, I think Frosch was the guy out
He
there.
was from Woods Hole.
Yeah, I think so. So anyway, we sent it down there, and within a month, General Motors had it all sorted out, made it work. So it was good.
You left a plaque to some of the crew.
We, yeah, this is a little side issue. We had a Belgian sculptor who did a little symbolic fallen astronaut for us. And you can see it here in this picture. And we decided we'd leave that as a memorial to all those, both Russian and US, that had died in the pursuit of space. And so then we had this little plaque made up with all the names on it. And Dave left this on the lunar surface. Turned out to be a little bit of a problem because a couple of months after the flight, we found out that there was an art shop in New York, Waddell. We're selling models of this fallen astronaut for $750. And they had made 1,000 of them. So that was a nice little payback to the sculptor who did that, even though one side claimed that he knew he was not supposed to, and he claimed that he'd never heard anything, that he couldn't. And it was just his word against hers, and kind of thing. So anyway, he stopped selling them. He has become a dear friend of mine. He's 93 years old. I stayed with him for 4 days last year when I was giving a talk in Amsterdam, or in Antwerp, to a UN committee that was meeting there, and I stayed with him. Wonderful guy, wonderful sculptor. He came over here a few years ago, the Smithsonian.
Yeah.
Were you there then, when he came over?
Yeah.
The Smithsonian had a big celebration for him here about 10 years ago, and he came over, and Smithsonian, everything is forgiven. But
Aerospace Museum, yeah.
Yeah, Aerospace Museum. Wonderful guy, but that's what this all was all about, was a memorial to those who'd lost their lives in the pursuit of space. Or actually, this memorial was those who had lost their lives in space, I believe.
Yeah.
Except I think we had the Apollo 1 crew on there too, didn't we?
Right.
Yeah, I don't remember. Larry, you probably remember who all the guys we have on it, but.
It had everyone.
Oh, I don't think we had Ted Freeman on there. Yeah.
That was about 3 or 4 weeks before, or a couple of months before Apollo 15, so that's when you guys composed it.
Yeah. Did we have Charlie Bassett on that? I forget. Okay, Bassett and Elliot C. Okay. I don't remember now.
So here's the Lem back.
Okay, here we
back down
come to kind of the final, and we'll wrap this up. After they'd been on the surface for 3 days, and I had had my joyride for 3 days without them, people have asked me a million times, wasn't it lonely up there by yourself? And I said, oh, you got to be kidding. No, that was the best time of flight. Well, why is it the best time of flight? Well, let me put it to you this way. Our spacecraft was 220 cubic feet of volume. That doesn't mean anything until I tell you that's the size of a Volkswagen Beetle. So if you can imagine getting 2 people and yourself inside a Volkswagen Beetle close the doors, and you stay there for 2 weeks, you'll have some understanding of what it was like with those two guys. So after 4.5 days with those guys, they went down to the lunar surface, and I thought, hallelujah, I got rid of those guys for a while. I can be all by myself. So I spent 3 glorious days by myself in lunar orbit, doing all the work. I worked about 20 hours a day. I only slept about 4 hours a night because you're only going to be there once. We're not going back. So you do everything plus. You do everything, and then you think up things to do, right? So I did that for 3 days. Dave comes back up into orbit, and I'll let you in on a little secret. Most people think that the 3 guys on a crew are blood brothers, that they're close as close can be, that they're all buddies, that they all do everything together. Not true. Dave and I never really got along that well, okay? But he was a commander, so we always did everything his way. During the training program, we'd come through all these procedures and flight plans and all that kind of stuff. And, you know, I developed my own ideas about how things should be done, and I'd talk them over with Dave, and we always ended up doing them his way. So I kept track of these things, because I didn't like that. So I get him out here 50 feet. Now, I'm in the vehicle that can come home. And I felt, you know, I got that sucker right where I want him. So he said, let's dock and finish up. And I said, no, I think you and I need to have a little discussion before you dock. Anyway, that just reminds you got to have a sense of humor, let me tell you. You got to have a sense of humor. As anybody knows who's been through the routine of going into space, Jeff, your own Jeff Hoffman here knows only too well, you got to have a sense of humor or you're not going to make it. You're not going to make it through. But you got to do all the right stuff too, but you got to have a sense of humor.
I want to have you say a few words about the EVA. So you did a EVA on the way back from the moon, the furthest away from Earth.
Right. That is the one Guinness record I have that will never be beaten, is I did the first deep space EVA. We had these 2 cameras in the scientific instrument module. One was the Icon, large register, high resolution camera, which had been designed originally for the U-2 program in this country, taking pictures from 60, 70,000 feet. It was declared obsolete, so we were able to carry it on our flight. The only thing we could not do, we're told very strongly, the one thing you cannot do is point it at Russia. And I thought, that's a strange thing. I mean, if I was at 60,000 feet taking pictures of Russia, I'd be a little concerned too. But if I'm at 240,000 miles taking a picture of Russia, I'm not sure we'd ever find anything on there that was any value to anybody. But anyway, we couldn't point at Russia. So we had this ball opticon camera that took high resolution pictures. I actually had pictures of the lunar rover on the surface. It's only less than 4 feet wide. Okay, so we got pictures of it. The other camera was a mapping camera that had a laser altimeter that recorded on each
frame exposure.
The exact altitude so that they could use that to make pretty accurate maps of the moon. So anyway, these are outside. They're out in that open bay, and it was my job to go out and retrieve those. So I went out twice. How many engineers we got in the room?
Quite a few.
All of them.
Oh, okay. I'm going to tell you a story. May I take a few more minutes? Okay. Got to tell you a story. When I got assigned to Apollo 15, the procedure for getting these film canisters back into the spacecraft was pretty well along the way, okay? One of the other astronauts who'd already made a flight was doing all the engineering work, and he had gone through several different procedures and different equipment. One was a long claw arm that, you know, they could, like a Canadair. But what he ended up going with, which if I hadn't said something, that's what we would use, was an endless clothesline. Now the idea was that I'd grab a stalk with a pulley on it and the endless clothesline wrapped around the pulley, and I'd carry that out with me, put it in a stanchion out there, and stretch out this endless clothesline. So then I'd go out there and I'd clip the film canister to the clothesline, and Jim would pull it back in. And I gave that a little thought, and I said, it'll never work. Never work. How have you tested this? Well, we've tested it thoroughly in the water tank. Well, how do you test a 90-pound canister in a water tank? Well, you make it out of Teflon, you cut a lot of holes in it, and you make it as neutrally buoyant as you can make it. And you think that's going to resemble what it is in space. Well, that's the best we could do. And I said, well, it won't work, and I'm going to prove it to you. So we get the zero-G airplane going, we get the mock-up, and we get all this stuff from the hatch to the back of the sim bay, or the back of the service module. And I go back there and I grab this 90-pound canister, I click it to the clothesline. Now we're doing these parabolas, so you're only getting about 30 seconds at a time, right? During the middle of one of those parabolas, the canister got about halfway back, and it started to sway back and forth because there's no atmosphere and there's no gravity, and it's 90 pounds. So if it starts moving in a direction, there's nothing out there to stop it except that clothesline. So it started whipping back and forth. It knocked an RCS quad right off the side of the service module. See? What do you think we ought to do? Okay, I said, I'm an engineer. But I'm an engineer that thinks the simplest way you can do something is the best way. So here's what I think we ought to do. I'll just go out and grab it and bring it back with my hand. Simplest thing. I mean, how could it get more simple than that, right? Well, they didn't like that because that was unsafe. Suppose I let go of it. So, okay, do a wrist tether with a hook on the end of it. And then if I let go of the canister, it's not going to go anywhere, right? Okay, so we go try that, and it works fine. A week later, the engineers come back to me and say, well, we're still not happy about the safety of that. So what we'd like to do is drill a hole in the hinge pin of the clip and put a pin in it so that there's no way that clip can come loose. Okay, so they put that in. And we went and tried it. And it was fine. 2 weeks later, they come back and they say, we're still not happy with it. What do you need? What do you want to do? Well, the pip pin that goes through the hole in the hinge, we want to drill a hole in the end of that. We want to put a cotter key in the hole so that the pin won't come out, so that the clip won't open, so that you... Oh, Jesus Christ. Okay. So that's what we did. That's what we did. The other thing about the EVA that I thought was kind of funny is I'm on an umbilical, and the umbilical is... Yeah. Okay, here you go. This is the only picture they got of me, by the way. They got 7,000 pictures of each other. And this is the one they got of me. Okay. So anyway, you think there wasn't a conspiracy back then? I got to tell you. So anyway, I'm on an umbilical, 5 psi. It's an open loop system. We've got a valve in the suit that relieves at 5 psi. Okay. So you get this pressure coming in. I don't know what the incoming pressure was. Probably 6, 7 pounds, something like that. And you relieve at 5 psi. Now, if for some reason the flow rate goes down, there's a warning tone. If the pressure goes down, there's a warning tone. Those are 2 things that can trigger it. What kind of signal did this guy, one of the astronauts before me, same guy who did the clothesline, right? And I kind of figured that's why I was sort of looking at it for a problem. It's just a tone. Just a tone. I don't think it'll work. Why? If you've ever listened to a monotone for more than 30 seconds, and you haven't forgotten all about it by the end of 30 seconds, I'll miss my guess. You do not retain a monotone. Oh, they said, I don't think that's a problem. I said, well, it is a problem, and I'm going to prove it to you. So I went in the vacuum chamber, had a whole raft of guys up in the control room. Chuck LaPinta was my doctor, and he was there. Ran the chamber down to vacuum. 5 psi, I'm sitting in the suit. I stuck my finger in the outflow valve because I wanted to drop the pressure in the suit to trigger the alarm, okay? So I get down to 3.5 psi, and the tone comes on. And I just held it there. And about a minute later, you couldn't hear it anymore. It was gone. So we ended up, well, and then I wanted to carry it a little bit further, so I kept lowering the pressure in the suit until I got down to 2.5. 2.5 is the theoretical limit that you can survive, okay? If you get down to 2.5, that's pretty bad. But I went down to 2.5 that day. Guess what? The sound disappeared completely. Why? Not enough molecules in the air to sustain the sound wave. Down to 2.5 psi. You're close to a vacuum. So what did we end up with? You ever heard a French police warbler? You cannot get away from it. You can hear it 5 miles away. And that's what we went with. Keep it simple. Keep it simple.
There's the painting of the picture that you wish you had taken.
Yeah, this is a painting by a guy by the name of Pierre Millon. And this painting is hanging very proudly in the Air and Space Museum in Washington. And when they don't have it on display, they have it very, very carefully secured away because it's one of their prize paintings. This guy is fabulous. Now, they would not let me take a camera out of my EVA. I argued and argued and argued. Oh, you got to take a camera. There might be things out there that we don't know about that we really need to have photographic proof of. And they couldn't figure out anything. So when I get back, I get Pierre and I get together, and we spent days and days and days going over, and he would draw this thing, and I'd give him what I saw out there. And the interesting thing is that if you look carefully alongside where the RCS quads are, you'll see some bubbling on the surface. They didn't think that would happen. So we told them something, that those RCS quads actually scorched the surface, so they had to be a little careful how they handled the surface of the service module. Interesting things and important things that we were to find out. They allowed cameras after me because we had sort of made the point.
Right.
But they wouldn't let me carry one out. I went out twice. I got the high resolution camera, film in. Then I got the mapping camera, film in. I went out a third time and put my feet in some foot restraints and just stood up and looked around. And it was kind of unbelievable because I could see both the Earth and the Moon at the same time. They're both sitting out there like that. Unbelievable.
Great.
Yeah.
Let's say something about the star field that is there with the star.
Yes. Starfield. We're getting in.
Yeah.
You got another 5 hours? Starfield. And I don't know what the real numbers are, but I'm going to give you some generalizations. But if you look through the sky here, I think you can count something like 10 to the 6 stars, is it, Jeff? Something like that? I don't know. But let's say. Huh?
Yes.
No, okay. Like a million, maybe? I don't know. No, it wouldn't even be a million. Anyway, there's no question that light comes through the atmosphere. A lot of it doesn't get all the way through. The more distant, well, the smaller, I mean, you know, the ones with less density or less intensity don't make it through the atmosphere. So you're not seeing all the stars that you could see if there were no atmosphere.
On a dark night in the desert, you'll see a couple of thousand stars.
Yeah, okay. Or down in Chile. If you go to the top of the mountain in Chile, you can see, actually, you can see the Gegenschein down there.
Less because your night vision decreases when you have less oxygen, but still
Yeah.
a couple of thousand.
Well, the funny part, Jeff, was that when I was in a pie-shaped section of my trajectory around the moon, I was shadowed from both the sun and from the Earth. So I had no light shining on me from anything we've got in our own system. Only light I had was from starlight. Now, we had 37 of the brightest stars that we used for navigation. Okay? They were always, and we spent all of our time in astronomy learning where those stars were and learning what the guide stars were to get us to those stars. So I get to this section in back of the moon where I'm shadowed from both the sun and from the Earth, and I'm looking at the star field out there, the universe out there the other way, and I could not find a single navigational star. All I saw was a wash of light. No single stars anywhere. I could see the horizon of the moon because of the light that was cut off. That's how I saw the horizon of the moon. Unbelievable. Millions of times more stars I could see out there than you can see through the atmosphere. So, the bottom line, and you're probably all familiar with Carl Sagan's story that became Contact. He always talked about, from a mathematical standpoint, there has to be life out there. No matter how many stars you see, there's going to be a percentage of them that are going to be the size of our sun. And of those, there are going to be a percentage of them that have a planetary system. And of those, there are going to be I could go on and on and on. But it doesn't make any difference how far you carry out that thinking. You get to the bottom, and there's at least one somewhere that's going to be ideal for life. So I got to thinking about that. We're in the Milky Way galaxy, and we're talking 400 billion stars. And we're talking another 200 billion galaxies out there. And I know, Larry, we're talking universes now, but how many universes are there out there? It's a good question. We think there's only one, but I've talked to astronomers who say, I'm really not sure. So we may be beginning to think in bigger terms than we've been taught all of our lives. It may be a whole different thing out there. Anybody seen Interstellar?
Oh, yeah.
Dumb movie, but anyway, it's fun. Yeah.
All right.
I happen to like Matthew McConaughey, so it was okay. I did not like Matt Dillon in that movie. He was a bad guy.
All right, so I'd like to use the remaining time to get questions from the students, and if you could use the mic, that would be best.
Yeah.
So I'll start with the students that are taking the class, and then we'll open up to a broader audience.
Okay.
All right, I got the first one.
He's too eager. This is going to be a good one.
Well, it's a fun one. It's a fun one. I promise. All right. So, as you may know, SpaceX announced they have a lunar tourism thing going on now. So
Maybe.
Maybe. All right, we'll see. But you mentioned earlier that before it was kind of being in like Volkswagen when you have two dudes, three dudes in a Volkswagen, and then you're all alone when everyone else went to the surface. So, little birdie tells me that the two people, it's a dude and his girlfriend from somewhere. And so I want to know what your opinion on tourism in space, and also specifically Blue Origin and SpaceX. Thank you.
I'm sorry.
Blue Origin and SpaceX and space tourism in general.
I think low Earth orbit space tourism is great. I suspect we'll have a Hilton hotel up there sometime. We've got lots of inflatables that would probably turn into modules for a nice little hotel up there. And I think that's great. Well, let's leave that to SpaceX and Blue Origin and maybe Boeing with the Starliner, Orbital ATK. We got a bunch of them. They're all going to be talking about that. It's kind of, I find it kind of interesting that we keep talking about civilian space programs like SpaceX. Guess who's paying SpaceX to do what they do? The U.S. government. So there's a part of me that says, why are we doing that? I mean, if we're going to pay them to do it, why don't we just go ahead and do it ourselves, right? On the other hand, I realize that when somebody like Elon Musk comes along, who is a brilliant individual, and he can design a system that not only launches but comes back and lands on the launch pad, then you got something going for you. And I don't think NASA would be very good at doing that, because we think in different terms. But I have been to his launches and watched his thing come back and land, and it's fantastic. Going to the moon. He's going to send 2 guys to the moon, around the moon, come back, and they're not going to have a pilot with them. I don't think I like that. Going to have no, if something goes wrong, forgive me. It's not the right thing.
Sir,
Yeah.
so this question is prompted by your story of the safety pin that had the safety pin in it. And
Right?
so I was intrigued actually in the book about the incident about 61 hours mission elapsed time when there was a water leak around the chlorination cap that created a ball of water in the spacecraft. And within about 17 minutes, you had it fixed with the help from the ground.
Sure.
Now, you said in the book that how did you put it? It was about that robots can't fix themselves. Machines can't fix themselves. And that's about the story of humans in the loop. So how would you comment on what's happening today, where some researchers are trying to work towards systems to be used on Mars, which are totally autonomous in preparation for humans going to Mars? How does that sit with your experience? Yeah.
I think that's an absolute natural progression. I think before you send people someplace, you send something that if it gets destroyed, it's not going to kill anybody, okay? So you send a robot to the moon, you send a car, you send a rover to Mars, and you do all you can with a rover. And while you're waiting for the manned program to mature enough so you can send the man, you keep sending these objects there, and they become more and more sophisticated along the way until you actually get to a point where, hey, maybe they're almost as good as a man. However, I will say, the problem with anything mechanical is garbage in, garbage out. A robot is only going to do what it's programmed to do. Now, I don't know, maybe we will end up with robots that can actually extrapolate and think on their own. I don't know, maybe that'll happen someday. But we don't have them now. So right now, anything you put into a software program is what you're going to get out. Give you an example. The water that you talked about. Well, there's one even more interesting than that. We lost a bowl of tomato soup one day. You know, it's interesting. We don't think about it a lot, but we basically rely on gravity for everything we do. Why is a spoon made the way it is? Did you ever think about it? Why is a spoon made the way it is? It's to hold the liquid in the spoon because of gravity. You get in space, you don't have gravity working for you, but you've got two other things. You've got adhesion of the liquid to the spoon, and you've got what's called surface tension, which encloses the ball of liquid on your spoon. And you can dip into a tomato soup, hold your spoon up, and you got a big ball of tomato soup on the end, and it's going to stay there. It's not going anywhere. If it's too hot, you let go of it. Let it float around for a while. It's going to come back around to you sooner or later. And you wait till it comes back around. If it's cooled off enough, you go ahead and eat it. Now, if you open that bag a little too fast, you break the surface tension, and a ball of tomato soup would come out. And it happened to us one day. We had a ball of soup, tomato soup come out. It's about as big as my fist. And it started floating around inside the spacecraft, okay? What do you do with a ball of tomato soup? And here's where I figure robots would never figure this out. Right. So you can't touch it, because if you touch it, you're going to break the surface tension. Now you got 1,000 little balls floating around. You can't, a straw won't do it, because that means you got to touch it. So what do you think we did? What's the best solution? Well, I'll tell you what we did. We got a towel wrapped around it, and we absorbed it. Robot would never think of that. That's why I say. Yeah, right. Had to wring it out of the towel, Jeff. No, but this is the. I think this is the world we're in.
Why don't you go to the mic?
We're sort of like on the first step of robotic emulation of what humans do. 100 years from now, it's going to be totally different. They're going to be much smarter. We might have interactive brains, all kinds of things. So I don't know, but right now we're not there. Yeah.
So this expands a little bit on your robot talk, but some had kind of questioned the scientific value of Apollo, especially at the beginning, and particularly the cost of sending humans to the moon.
A value?
The scientific value.
Scientific
value of Apollo and going to the moon, and particularly the cost of sending humans, the additional cost of sending humans to the moon. How important was the human aspect of being on the moon and encircling the moon and getting that up-close observational input from a human?
There's no substitute for a pair of eyes. You can't. You just can't do it unless you've got a thinking brain and a trained individual doing that work. I don't think you could ever develop a mechanical device that could interpret things that you see, extrapolate stuff, and figure out ahead, think ahead about what you're doing. I think the value of the scientific value of what we did on the moon, I think there's a real value to it, but the real value to it is only in the context of what we're going to do next, in my mind. We've got to go to Mars, okay? We may have to go to an asteroid in the meantime, I don't know. But I believe that what we've done on the moon, and number one, we're really kind of zeroing in on how'd the moon get there? You know, what's the genesis of the moon? How did it get there? And I think we're leaning more and more about the Pacific Ocean, are we not?
Yep. Right.
There's an object that came by Earth, gravitational
Pull.
effects
Interaction, yeah.
pulled a big chunk out of the Earth, and that became the moon. I think that's the way. That's kind of where people are going today. So but we got to think about these things, and I don't think we would find out that much about the moon if we just had robots there. If we're just doing Mars Curiosity stuff, we're just taking pictures. Well, there's a few things too, but we're finding out what the surface is like, but maybe not a lot of stuff that we really need to know down the line.
Kind of related to that, I've read a JPL document that quoted a figure of the entire daily productivity of a Martian rover could be achieved in 45 seconds by a human geologist. So how do you think the future exploration of Mars, how do you think the geological discoveries that we'll make are likely to change once we have a human crew there instead of these robotic rovers?
I got to tell you, I have a very different attitude about all that. We're going to get to Mars. I don't know when. Might be 10 years, might be 30 years, it might be 100 years. I don't know, and I don't care. Because in the long term of events, it doesn't make any difference. If we get to Mars in 1,000 years, we're still going to be fine. If we get to Mars in 1,000,000 years, we're still going to be fine. It doesn't make any difference. Because Mars is not our goal. Mars is a step along the way. And getting to Mars is just one more step towards where we really need to be. And that's on another planet, like ours. So all this talk about, and I think it's very important that we promote the exploration side, because that's how you get the population to say, oh, that's a great idea, let's put some money in it to go do that. But what the underlying cost to me is that gives us another capability. Then the next step is a little further out, and the next step's a little further out, and pretty soon we're going someplace that we can live. Because we know we can't live here. The day will come. I mean, there's only so much hydrogen in the sun. And, it's pretty well calculated now how long the sun's going to last before it burns out. And maybe another 3, 4, 5 billion years. I don't know. Jeff, you probably have numbers better than mine. 5 billion? Mm-hmm. Okay, yeah. 5 billion years from now, we won't be able to live here anymore. Now, if we haven't killed each other all off by then, whatever population survives 5 billion years from now is going to have to go somewhere else. So we better have a capability to do that. And I say what we're doing today is the very, very, very tiny little steps in that direction. You know the old Chinese theorem. A trip of 1,000 miles starts with one step. And that's kind of where we are in space, that first step.
So I would like to add from the scientific point of view, indeed, all of the methodology of observation has improved a great deal since the Apollo time, and that's the way it should be. Every generation picks it a little further out. So the instruments that have been floating around on the surface of Mars are 10 times better than anything that we had during the Apollo years, which is fine. And we were able to learn a little more about the color of the Martian surface and that. What's the reason behind that color and where the ice might be and how thick it might be and where, and all of that is wonderful. So the developments in unmanned technologies are developing very well throughout this planetary exploration time. And we wish to see that this continues so that there will be further development so we can send these things much further out. As he said, that the time scale of our lifetime is irrelevant. So we need to make sure that this is the path to the future.
More questions?
I have a follow-on to that last point. So what are the discoveries that you think we'll make on Mars from a geological standpoint with human exploration that we wouldn't make with robotic exploration?
With human exploration?
Yeah.
But as we just said in the Apollo program, there was a limit to what we can say from photographs or observations from whatever we have from the instruments to what the humans that flew either around Mars or around the moon or on the surface have made vast differences because of the human ability, because of the ability of the human eye to distinguish all kinds of things and colors and so on, and the human mind, the interaction between the two to point to certain things. There is no comparison. The human mind and the human capabilities add a great deal to the instruments.
Mm-hmm. Sarah?
Yeah.
Professor El Baz.
And talk closer to the mic.
Yeah.
Sorry, I'm short.
Put it
Yeah,
down.
good,
Put
good.
it down.
Go ahead.
She's an Air Force officer.
Yeah,
too.
that's good.
Air Force,
Air Force.
Yes, sir. Thank you.
what do you fly?
So I'm a flight test engineer. Worked on C-17
Okay.
and KC-135
All right.
before
That's
I came
just
here.
as good. We won't need,
Thank you.
with all these robots going around, we won't need pilots in another 10 years anyway.
We'll need them for a little while longer. So regarding the moon, do you think there's still more to learn as far as geology on the moon? And will it take further manned expeditions to get there, or do you think we can do with the orbiters and landers?
Well, there are all kinds of things that we can do with the unmanned instruments from orbit, and there are all kinds of things that we can do from moon, but there is a great deal about the moon that we have not really learned about, from the original crust and the far side composition, the crust in the southern portion of the moon. There are several questions about the moon, including the origin, the original, whether the moon was the wife of the Earth, or the child of the Earth, or the girlfriend of the Earth. All of these theories are still floating together. So there is a great deal to discuss about the moon from the scientific point of view, concerning the exact origin, the exact composition, and how it changed with time.
You know, it's interesting, and you can correct me if I'm...
It's okay, I will.
The light elements are gone from the surface of the moon.
Mm-hmm.
Why? Because the mean free molecular velocity of those light elements is faster than the escape velocity of the moon.
Mm-hmm.
Not faster than the escape velocity here on Earth, and that's why we've retained an atmosphere and the surface that we have. But on the moon, you're seeing much heavier elements because the light ones are all gone.
Including an atmosphere.
Yeah, or including the atmosphere, right, exactly.
So what landing sites would you go back to, or which
I would
ones?
send him to the far side to where he had picked up very good sites in the Tchaikovsky and the Moscovians, and there are places on the far side.
But I would need a flying machine to get around.
Okay, we'll give you one.
You give me one.
Hi, thank you so much for being here today. My question for you is, when you were deciding where exactly to land on the moon, how did you manage a lot of the risk involved? Because I feel like you had some very limited information in terms of defining where to land. And what was the most surprising thing that you found once you landed on the moon?
Yeah, we sent pilots to the moon, and we had lots of pilots. So if these are not made, then make it. Then there are others to make it. So, but you didn't worry about that. No, the landing site studies were very thorough, knowing that there is absolutely no potential for any error that would make that landing site less safe than something else. So we were absolutely certain that all of the calculations would give you this location and that location. We knew as a geologist that it is absolutely certain and such and such. And the only problem that we had was with Apollo 11, and it had nothing to do with the geology. It had to do with the velocity at the time of separation. So the spacecraft took them further out from the selected site, and therefore Neil Armstrong had to fly by hand to get away from a rock field. But everything else was studied very thoroughly beforehand to make sure that the geology permits a safe landing site within a proper area for the rest of the mission to be undertaken. So there was really no question about that. And as far as what would happen if they did not do it, because they are pilots, they knew how to maneuver, and they could, even if they came all the way down, and were able to find that there is no spot for him, there is a way to lift off.
Just one simple little thing. The last 25 feet of every single lunar landing we made during the Apollo program, the commander of that flight had to fly it the last 25 feet.
By hand.
You had to have a man there. You could not have done it robotically, because they would have landed on a rock.
Mm-hmm. Apollo 11.
Or a crater or something, which again, a robot wouldn't know what to do about.
Thank you.
Mm-hmm.
Come on, and Rocky, you have a question, I think, and a few others. I want to make sure everyone from the class gets in.
With the J missions of the Apollo program, you saw the start of the integration of science-trained and test pilot-trained astronauts. Can you comment on the early cultural relationships between those two types of astronauts and whether there are any challenges integrating crews of science-trained versus test pilot-trained people on these ships.
You're talking about the progression of what was required of somebody flying as when we started the program through like the Apollo program?
Yes, and then
That's the
culminating
question
with
you're
Apollo 17 with Jack Schmidt being a geologist trained, and then more and more into the shuttle program, we have science trained and pilot trained people working together.
I have nothing against Jack. Okay.
I do.
Jack, yeah, I know. Jack's okay. He was a geologist. However, if you were to take the science that was done by Jack on 17, compare that to the science that was done by Dave Scott and Jim Irwin on Apollo 15, I think you'd see a big difference because Dave and Jim were absolutely focused on the geology. And Jack is a trained geologist, so it was just another kind of another geology thing to him. But with Dave and Jim, they were absolutely focused on doing this, on doing the geology. Now, let me make a comment too. The original Mercury guys, all 7 of them, there weren't any academics in the group. They're all pilots. They're all test pilots. The next group that came in would be Tom Stafford and Frank Borman and those guys. Now we're feeding in more and more academics. Frank Borman, as an example, was one of my instructors at West Point when I was there. So he was a professor at West Point. Very, very smart guy. I think Tom Stafford is one of the smartest guys there is. They didn't have all the advanced degrees, but they were a step up. Then they got the third group, guys like Bill Anders, who was a graduate nuclear engineer. And they got a bunch of guys like that. My group came along, 19 of us, I don't know. We were all PhDs and multiple master's degrees because we were selected into the Apollo program. So they really looked at the academic background. And we also had to have the flying too, but we let guys in that were not test pilots because they had PhDs, okay? So it was kind of a mix. But the emphasis, you could see the emphasis shifting during the Mercury, Gemini, and the first part of the Apollo program, that more and more academic excellence was required of the people that flew on those flights. So that's how now we go to the shuttle program. Now you have a very clear split. You got 2 pilots up front, you got 5 scientists in the back. We don't have to worry about a pilot being a scientist, okay? We can separate them out. Space station the same way. We don't even need pilots to the space station. How long has it been since we've sent a pilot to the space station? Yeah. Scott Kelly was probably the last one. Yeah. Okay? We don't do that. They don't need it. Now we go to Mars, and however they're going to do it, and I have real problems with what they're talking about, but they're going to send probably 4 people in the Orion spacecraft. In fact, they're not even going to go in the Orion. They're going to leave that in Earth orbit. Did you know that?
I think they're still trying to figure out the...
I think they are too, but that's the last I heard, because the Orion is not capable of going to the Mars and back. Yeah. Okay? It's a bad vehicle, bad machine. Built like Apollo, which is not good. Apollo would come back from the moon, no problem. Do y'all know what L/D means?
Sure.
Sure. Everybody knows what lift to drag. If I fly a Cessna, I'm going to have a lift to drag of probably 8 to 1. If I fly a U-2, it's 30 to 1. If I fly a really, really good glider, it's 40 to 1. I got lots and lots of time in what's called an F-104 Starfighter. It's got an L/D of 4 to 1. You better know what you're doing when you land that thing, because it's coming down like a rock. L/D of Apollo was 0.27, which meant you got a little lift, but it's like taking an airplane and turning the wing 87 degrees into the airflow. Okay, that airflow is going to go down that 3-degree incline, and it's going to give you a little lift. It's more Newtonian than anything else at first. So in Apollo, we could come back at 17,500, we're okay. And we could do cross-range maneuvering up to about 1,500 miles, okay, with that. L/D of 0.27, which is the new Orion that they're talking about, coming back from Mars at 35,000 miles an hour, does not have enough lift to stay in the atmosphere. Got 1 or 2 things. Either burn it up on atmosphere, if you're too steep, or you skip out of the atmosphere, go to what they call a high key, slow down, and then come back in a second time. This is a make-around for the lack of capability of the spacecraft. Okay? So we got some problems. We got some problems that got to be solved. And I'm not, personally not happy with the direction they're going, because they're building Orion, which looks like Apollo, and that's why they built the Orion, because it looks like Apollo. And that's all they knew how to do. SpaceX, Dragon, it's another one. Boeing, Starliner, another one. They all look like Apollo. Enough said.
They keep
my
thinking
pet peeves.
They keep thinking Apollo worked, so let's do something.
Yeah,
like
but it worked coming back from the moon at 17.5. It didn't have to come back from Mars at 35. That's the problem.
Good afternoon, sir.
Hi.
Thank you for being here. My question would be about simulation and training.
About what?
About simulation and training. So you mentioned in your book that you were training for disaster and that a normal flight would be a piece of cake. And at the same time, that a big chunk of this training, I'm not talking about the scientific training, but the technical training was also very tedious, but with some parts which would be more exciting. So what was the single most useful part of the training that you felt was really helped you during the flight?
Well, I could answer that one or two ways. The most interesting part of our training was flying a T-38 from Houston to wherever we're going to train. That was the most fun part, and that's what really kept us going. Simulator training. I got 1,500 hours of flying a simulator over a 3-year period. That's 500 hours a year, which is 25% of my time. That's 8 to 10 to 12 hours at a time sitting or laying in a simulator to go through a, you can't compress the time that it takes to do a maneuver in space. You got to do it in real time. Otherwise, it doesn't mean anything. So if I'm doing a rendezvous and docking, it's going to take 10 hours. I got to be there 10 hours. That gets pretty boring. I got to tell you, you just lay there. In fact, we had a guy, Jack Swigert was a good friend of mine. He was on Apollo 13. Unfortunately, died back in '89, I think, after he got elected to Congress. Jack was famous for doing all these simulations and falling asleep during launch in the simulation. And that's the way guys got it. You had to do the simulations. It's the only way you're going to learn. The only thing, we had the best simulators in the world. They were absolutely fantastic. They were 3D. I could look out a window in the command module, and if I moved my head, I could look down the length of the nose of the command module, just like you would if it was a real thing. It's 3D. I don't know how they did it. It was unbelievably good. So they were very realistic. The noises and the vibrations were all there. The only thing we didn't have was the G-forces, and we didn't have the vacuum. But everything else was great. Now, the most boring training of all was geology classroom. Because it was just, you look at a rock, and you look at a rock, and you look at a rock, and you're hearing all this stuff. The field trips were fabulous. I have to tell you. We did field trips in Hawaii, Alaska, Iceland, Mexico, the great Southwest, Oregon. We hit all the great spots, right? And they were always so much fun. I spent 10 days in Iceland. We went to the outback in Iceland. We went clear to the north coast in Iceland, which is a town that was awake 24 hours a day because the sun shone 24 hours a day when we were there. So at 3 o'clock in the morning, you go down to Main Street, and there's a whole crowd down there window shopping. These were the fun things that we did. Just a little side comment. I had a deal with, I had 2 geology instructors, Gordon Swan and Tim Haight, and we had a deal. And the deal was that when we went on a field trip, one of us had to take a bottle of vodka. It had to be a certain kind. Had to be a bottle of Oso Negro, which is a Mexican vodka. And we'd sit around the campfire at night, and the 3 of us would have our little touch of vodka, and everybody else would want some, and we wouldn't let them have any. So we went through all of our training program. So when my flight comes along, we're trying to figure out, how do I get a bottle of vodka on your flight, right? So we tried everything. We even tried to freeze dry it. You know what happens when you freeze dry vodka? It's gone. There's nothing left. The first thing that boils off is the vodka. And what you have left is just water. So that didn't work. So anyway, these are the kind of things. These are the fun things that keep you going, okay? Like I said earlier, you got to have a sense of humor. Because if you don't maintain a sense of humor through all this training, which is long and endless, I spent 70 hours a week for 3 years training for my flight. All the way through. That's what it takes. And you got to stay awake when you really want to go to sleep. Sorry, I hope that answered your question.
So building off the topic of training and talking about given your extensive training in both geology and also the field trips, the astronauts must have had a pretty good idea on what the moon looked like. So I'm curious about what was the most unexpected thing when you actually saw the real-life visualization of the moon.
Most unexpected thing that I saw, I'd have to say the universe. Most wonderful thing I saw was the Earth. And I saw that come up over the moon's horizon 75 times, okay? And I always got to a window and looked at the Earth. But the most awesome thing and the thing that really, really got my imagination was looking at the universe out there. That is so unbelievable. And then you begin to understand what it's all about and where we are and what we're part of, and that there's so much more out there. That's what's mind-blowing. I can understand the Earth and the moon being in orbit around the Earth, and the Earth being in orbit around the sun, right? Hey, that's pretty small potatoes. When you look at the rest of the universe out there, it just blows your mind.
From over the far side, looking at where there's neither the sun nor the Earth is in view.
Hi, thank you for coming here today. Looking ahead to the future, both of you have a lot of experience either being a CMP or training CMPs during the Apollo program to identify surface features. But looking ahead to Mars, to what we might want to do there, we have different assets around Mars that we do around the moon. We have orbiters with high-definition imaging. We also have an atmosphere that could pose some visualization problems. And you said before, you know, we don't want to do things like Apollo. So what would you change in the training of someone like a pilot to sort of do that same sort of job that we have to do in Apollo, but for Mars, considering the different features and different assets we have there?
Maybe I misquoted a little bit. The only thing I would change would be the machinery. What we do when we get to Mars, we're going to have to do what we did at the moon. I think it's going to be the same kind of thing. We're going to be looking for the same kinds of things, maybe a little different things on Mars, because there might be some water, might be some other minerals, that kind of thing. Okay, so we're going to be looking for specific things on Mars, but the crew's going to be the same. I guess my concern or dismay is how we're going to get there. I don't think that's right. But I'm pretty outspoken about that. I actually took a program to NASA headquarters and presented them with a reentry vehicle that had an L/D of 1.75. And they turned it down. Why? Because they had built Apollo and they knew how to do that. That's nonsense. There's no creativity. You got to have a paradigm shift out there. You got to be brave enough to make big decisions and take a big risk. Because if you don't do that, you're not going to get anywhere. That's my feeling. Yeah.
Well, I'm sold on going to Mars, but how do you think we can kind of convince the public or, you know, the government to spend that kind of money to get to Mars? I feel like there's definitely a perception that public interest in space waned after Apollo, and it's just never come back in the same way.
Well, to be very blunt, I don't think I'd do anything. Except I think I'd talk to some of my Russian buddies or Chinese. And let's start talking about a program to go to Mars. And that they're going to do it in the next 5 years. And that if we don't get on the ball, they're going to beat us. Mm-hmm. And that kind of information takes care of itself. I wouldn't have to market going to Mars at all. I don't know. I don't even know that that's the right approach, but that's what got us to the moon. And so maybe that's the kind of thing that we need to get us to Mars. I don't know.
And this time it will be the Chinese.
Go ahead.
Hi, sir. Very honored to be in your presence today. Did this extraordinary trip change your vision about humanity, and how did it change, if it changed anything, your vision about human beings when you came back? Did it change anything in your personal life?
You understand what she said?
Yeah, what the trip going out there, how did it change you? And
Oh, how did my trip change my life?
Your view of humanity.
Humanity.
My view of humanity.
Yeah.
Humanity needs to start thinking more about itself and its survival. We got too many things going on. We got too many people that like to wipe out other people. We got too much dissension, too much hatred. We're not going to survive as a human race for 5 billion years until the sun burns out if we don't take care of some of these problems. So, yeah, that's kind of what you come back with, is that, you know, all this stuff is so stupid and silly and destructive. We're not going to advance unless we can get beyond that somehow. And I don't know how to do that. But these are some of the ideas that you pick up on the way. Somehow we've got to solve some of these problems we got, or we're never going to get to 5 billion years. We're going to have World War Z all over again. Have anybody seen World War Z?
Go ahead. Hi, thank you so much for being here. So you mentioned, looking at humanity's survival over time and getting to learn about
closer to the mic.
Taking care of humanity and our planet. And you also mentioned, how incredible it was to see the Earth from the moon. So a lot has been said about how, the Apollo missions kind of coincided with a lot of the environmental initiatives going on in the 1970s. And I wonder how much you think, or how much of an effect the Apollo missions had on conservation and how we look at taking care of our planet and like treating each other.
I'm sure I understand.
The impact on the
environmentalism. I'm not sure.
Yeah. Can I say something first?
Please.
That's during the 60s, there was this incredible feeling of the United States of America's position in the world. And within NASA, myself and the guys that are working in my scheme, most of the NASA people were only in the mid-20s. And the question at the time was, are we going to let the Soviet Union, or the Soviets beat us? And when you discussed with some other person during the planning for the mission or something, and you needed information, and you looked to the other guys and say, go ahead, goddammit, go do it and do it right and do it fast. You want the Ruskies to beat us? And this is kind of the feeling that was permeated during this whole time, that we are going to send a man to the moon, bring him back safely to the Earth within this decade. So it was a statement from President Kennedy that kind of built up the national courage and then precipitated that incredible feeling of solidarity within the NASA group, particularly the young people like you guys sitting right here. This was just like you, faces like that, the ones that did it. The astronauts were a little older than you guys, but the ones that ran,
a lot older.
yeah, but the ones that really ran the whole machine, and the guys that fixed the Apollo 11, the problems with Apollo 11, and Steve Bales was an MIT graduate, 26 years old. All of these guys were that kind, and they were all pumped up by the fact that we are going to do it, and we are the best, and we're going to show the world, and they did. So what we really need now is not to lie down and say, well, somebody will do it or something. No, you need to reinvigorate yourself with this feeling, and this might require some leader of ours, not the present one, but some leader in the U.S. to pull all the people around together for an objective to do something super fantastic, including a space mission to Mars or to anything else. It doesn't really matter, but it matters that we can utilize all of the energy and the understanding and the vision and so on of the young generation that's right here.
You know what the average age in mission control was when I flew?
Yeah.
26.
Yeah.
Apollo 11, the guy who made the decision that the error signal they got, don't worry about it, keep going, was 22. You folks in this room, man, you're right there.
Yeah.
Okay? We need you people.
And it's up to you. All the future is up to you.
Young people who are thoughtful people, who will do the right thing at the right time, and who are not afraid of making decisions. Don't be afraid of making decisions, even if they're wrong.
Compete with the best.
That's right.
Okay, we'll do one more question.
Yeah, one more.
Hi, so thank you so much for coming. My question is about the role of doctors in medicine during your mission. Your book had a couple of funny stories.
Yes, doctors.
Yes, I wanted to ask about.
Oh God, we better have another half hour. No, go ahead.
Yeah, so you had a couple of funny stories, and obviously showing the mistrust between the astronauts and the doctors, and them not letting you know about why you had to take sleeping pills when you really didn't want to. You had a couple of funny stories. So is this stemming from maybe test pilots from back in the day being afraid of taking their wings, getting their wings taken away, or is there some other reason?
No.
Or
Okay. Backing up one step, as a pilot in the Air Force, I had a flight surgeon. He was there, right, on base. And his job was to keep me healthy, and if I had something wrong with me that would prevent me from flying, he was to write out a little thing that says, you're grounded. I get to Houston, and I've got a flight surgeon that's exactly like that. His job is to, in fact, the flight surgeon, if you've ever seen a television show called MASH, which is in Korea, my flight surgeon was one of the guys that MASH was made from off the Korean War. And his job was to keep me healthy, and if I got something that I couldn't fly, then he'd take me off flight status. We had another brand of doctors called mission doctors. Their job was to find experiments that they could do on us in flight so that they would find out more and more and more about the human physiology in flight. These were the guys we avoided, we did not trust, we'd have nothing to do with, because they looked at us as guinea pigs. No, this is kind of a serious one. On my flight, those mission doctors wanted to catheterize one of us in flight because they wanted to look inside the heart of somebody in space. Oh my God, you don't really mean that, do you? Yeah, we do. No way. You cannot put a catheter in me. We won't allow it. Well, it's perfectly safe. We said, we don't care. It's not something we think is safe. Well, let us prove it to you. And then you can make your decision. You know the story, Jeff? So they get one of their flight surgeons and they catheterized him. They put him on a bicycle ergometer, which is what we were using back in the day. He started pumping and pumping, and a little friction and pumping harder, and a little friction and pumping harder. 5 minutes into the protocol, he had a massive heart attack. You cannot do that to the human body. I don't care who you are. You can't put something foreign into the heart and stress it and expect that person to stay alive. You can't do it. So, yeah, we have a problem with doctors. Absolutely. I don't anymore because I'm not flying. But anyway, no, but
it's probably worth pointing out that Shannon Lucid actually did that on a shuttle flight.
Did she?
Yeah.
Catheterized?
And the complete ascent.
She was
from
catheterized?
launch. Yeah. Yeah.
Well, I'm glad it was her, not me.
Spaceflight 1 and Spaceflight 2.
Okay.
SLS 1 and SLS 2.
I think that's a very dangerous procedure.
Yeah.
Protocol.
And Shannon came from the flight very thin and kind of dazed.
I don't know.
Well, we need to wrap up. Let's give our guests a round of applause. Thank you. Thank you very much. Thank you. Thank you.
You're a good bunch. Thank you for setting through all this.